Welcome to a video on free energy and equilibrium. How are these two things related? I'm Dr. Ryan Hayes from Andrews University in the Department of Chemistry and Biochemistry, and we're going to see how these two things are related to each other. So how is delta G, Gibbs Free Energy, related to equilibrium constant? So in this video, we're going to figure out the relationship between, in mathematical and chemical relationship between delta G and the equilibrium constant, and probably look at the equilibrium constant at different temperatures if we get a chance, and also how do we determine the free energy for not at equilibrium. Very important. Why are these things important? Well, it turns out all of life depends on the Gibbs free energy of a chemical reaction, and specifically when they're not at equilibrium. Why is that so important? In fact, you're going to start to see here, this is a table from a recent biochemistry textbook. It talks about the standard free energy changes that go along with the glycolysis cycle. And there are 10 chemical reactions that are partnered together. So this is the coupling of chemical reactions. And we can see there is a delta G with a not symbol, a little circle, a superscript, and a delta G that does not have a not symbol. So we're going to discuss the differences between the two, and let this be our motivation that life is based on non-equilibrium spontaneous chemical reactions. How is that? How can we explain this? It all starts with our thermodynamic evaluation of free energy and how it relates to the equilibrium constant. So let's see if we can discuss the relationship between the two conceptually first to see if we can understand how they're related. So it's important to understand that the free energy, Gibbs free energy, is related to the reactants and how they convert to products. So we've already discussed this in other videos, and so you can look around and find those. And so since there's a relationship on how well the reaction goes and its connection with delta G, Gibbs free energy, there's also been a relationship on the amount of products formed versus the concentration reactants in a value that we call the equilibrium constant, K. So conceptually, these things are kind of related already. So we can see something about the favorability of a chemical reaction when we think of delta G and K. So hopefully you remember some things about the equilibrium constant. In fact, here's a question for you to ponder. If the equilibrium constant is greater than 1, what would you expect the sign of the free energy to be? Just as a big hint, an equilibrium constant greater than 1 means the reaction is product favored. You want to make a lot of products. What do you think? Normally this is when I would have students click in, but you don't have to do that now. We're not clicking in, just wanted to know what you would think. All right, so maybe you've thought about it for a second. Pause the video if you need to. The answer coming up. And the answer is B, negative. Students from some past classes have figured that out and remembered that a spontaneous chemical reaction with a negative delta G means you're making products, and that you're going to have a lot of products being made, and that's product favored with an equilibrium constant greater than 1. As you can see here, 73% in 2017 responded with B, the correct answer. So good job. Hopefully that was you as well. Well, how are these related? Well, we're just going to start throwing out some equations and not necessarily derive where they came from and how they came about. That's not necessarily relevant, but just to see that there is a connection there. So conceptually, they're definitely connected, but how are they related mathematically? And there is a mathematical formula where delta G naught, so this symbol is going to become very important in this discussion here, is equal to negative R times T ln of K. So this is the gas constant R, which is in joules per Kelvin mole, 8.314 joules per Kelvin mole, times T, the temperature. Oh, I wonder what scale we should do that in. Celsius, Fahrenheit, Kelvin, the Rankine scale. And this is ln, the natural log function of K, the equilibrium constant. Well, I wonder what units we should do the temperature in. And you can think about that. I hope it's obvious because it's in the R constant there that we should do this in Kelvin. All right, so we're going to look at this equation and practice a few problems. So the equilibrium constant for this particular chemical reaction right here, N2O4 as a gas going to make two NO2s, has a delta G of 5.370 kilojoules. Now, in order to solve for the equilibrium constant, I can use our formula, delta G naught is equal to negative RT ln K, and I'm putting in 8.3145, I got at least 5 sig digs there, joules per Kelvin, and for my R. Temperature, we're going to use, since it's at standard conditions, no temperature was given, that means 25 degrees Celsius. Plus 273 gives me 298.2 Kelvin. Now notice I went ahead and already converted the kilojoules to joules so that my joules and joules here will all match up in terms of units. The units help me to decide what I should do next. So that's very important. Now I'm going to divide both sides by 8.3145 and 298.2, essentially moving these two values along with the negative sign over to one side of the equation, which ends up over here. So that gives me then the natural log of the equilibrium constant is equal to these numbers. So now my joules will cancel out and my Kelvin will cancel out, and I'll get a unitless number. And then all I need to do with that number is take the exponential function, which undoes the natural log of both sides. It gives me 0.11. So you should stop right now and try to do this on your calculator, see if you get the same answers. If you do not, and you have some questions on that, please contact me at hayesr@andrews.edu. And so I'm willing to help give you some more detailed help. So notice here that we have a delta G that's positive, and that gave us a number for K. Yes, it's positive, but for K's, we really want to think about those numbers, how they relate to 1. Because if it's greater than 1, we said it was product favored. If it's less than 1, it is reactant favored. So equilibrium constants, 1 is sort of our reference. For delta G's, 0 is our reference because we're dealing with numbers that are positive and negative for Gibbs free energy. Equilibrium constants, we're dealing with numbers that are always positive, but they are either greater than 1 or less than 1. Okay, so we see the connection here. A positive delta G is an equilibrium constant less than 1. So this is the same chemical reaction. If this was endothermic, ooh, what do we know about this one? Ooh, we just know that it is a positive delta G. Is the reaction spontaneous? Spontaneous at low temperatures, but not at high temperatures. Spontaneous at high, but not at low. Never spontaneous. Ooh, what do you think? Well, we have a positive delta G, and it says here the reaction is endothermic. Ooh, how are you supposed to think about this? Well, we need to remember how the signs of delta H and delta S relate, and then also where are we with our delta G. So if this is endothermic, so this is where heat is going in, what is this in terms of delta S? Well, delta S, our entropy is going from, we're looking at the molecule, there's N2O4 is 1, going to make 2. So this is a spreading out. So this is a positive delta S. Positive delta S, positive delta H. This is a temperature dependent chemical reaction. So high temperatures or low temperatures are favored. Well, if you are dealing with a chemical system that is expanding here, then that will be favored at higher temperatures for the Gibbs free energy term. So it's helpful to go back to the delta G equals delta H minus T delta S. So it was kind of hard. You can't really go back to this equation and answer this question. I think that's what makes this one hard. This one's actually spontaneous at high temperatures, and our students were able to figure that out in 2017, so good job. So it's important though, even though we've got some valuable information with the Gibbs free energy and the equilibrium constant, we actually still need to go back to answer this one and understand delta H and delta S. So I have other videos on that that you can go watch. Okay, good job, students there. There is a temperature relationship between the equilibrium constant and delta G, but we've really got to factor that in with the enthalpy and the entropy. So what do you mean? Well, let's say you've got the same chemical reaction of N2O4 going to make NO2, so dinitrogen tetraoxide going to make nitrogen dioxide. So let's say we wanted to figure out what's the equilibrium constant for this chemical reaction at 100 degrees Celsius, or 373 Kelvin. Well, there's an assumption that if the enthalpy and entropy are not changing, we can just recalculate the Gibbs free energy at this new temperature using delta H minus T delta S. So I can plug in the enthalpy in joules. So I multiplied by 1,000 to get to my joules, plug it in the temperature, and I probably should have had another significant digit there. And then I plugged in the entropy. So all my units now, because the Kelvin will cancel out, and I'll be left with joules per mole. That's okay. And you can see that it's a negative 7,877 kilojoules. Now I can go back and rearrange my Gibbs free energy and equilibrium expression here and plug in the temperature and our new delta G and come up with, and here's our R, and calculate a new equilibrium constant. Well, this is at least the what ln of k equals, and then I take e to both sides and I get 12.66. So this is now a number that's greater than 1. So as I increase the temperature, the entropy term started to dominate. This is an entropy driven chemical reaction, and that helped make Gibbs free energy negative, which gave me a k greater than 1. So we now see an instance here with a Gibbs free energy that's negative and our k is greater than 1. Those are the key numbers to think about. So let's say you're doing a solubility experiment in the lab and you really need to figure out the equilibrium constant. What are you going to need to know to calculate k? So here's 4 options: G, H, S, Gibbs free energy, enthalpy, or maybe you need all of them to figure this out. Okay, I'd have my students click in, and this is what some have sent over the years. Delta G. Okay, and you can see here 68%. A lot of them answered D, which was what? All of the above. All the above. Well, that kind of could see what makes sense where you would want to know all of them, but from this formula, you need delta G for sure. And so there might be some truth to knowing all of them would really help for sure. So our students are making good observations here. So the students often, when I give this lecture, go into the lab to dissolve urea and figure out the thermodynamics there. And so there's a way in the lab to figure out the enthalpy of a solution by measuring the temperature, so they can get delta H. If they somehow knew the equilibrium constant, which then allowed them to get the free energy, if you know delta H, K, and delta G, what's left that you could calculate for? Okay, our students would be clicking in here, and hopefully you figured out the only thing that you don't know at this point is entropy S. So then using calorimetry to get delta H, there is a solubility experiment to get K. We could figure out equilibrium constant and thus Gibbs free energy and delta S. So this is kind of things we would do in the lab. So we want to put all of these different chemical reactions together. Our students in 2017 were able to figure this out. So that's good. All right. Now, do you know what this little circle means as a superscript up here? What do you think? Well, hopefully you correctly identified it to mean standard conditions. It often is used as degrees, maybe like degrees Celsius. But here, when we see it not associated with the letter C, this is a notation in chemistry to mean standard conditions. And that's going to be important here. Now, I like to throw in this question to see if students remember for a dispersing chemical reaction, the dissolution, like dissolving something, and that means delta S is positive, you're spreading it out. What's the sign of delta H? So I had taught this in some previous lessons. I wanted to see if they still remembered the connection here. What do you think? All right, hopefully you've had some time to think about it. And the answer is, you can't tell. Do you remember? Our students didn't remember. They have a hard time remembering these chemical concepts. That's why I like to review them. There's no connection between a dispersing chemical reaction, the entropy, and the enthalpy. We got to remember that. So I have a whole video, and if you can tell the difference between entropy and enthalpy, please go watch that. All right, so now that we know that there's a relationship between the equilibrium constant K and Gibbs free energy, what would we do if the chemical reactions were not under equilibrium conditions? Because we can just start throwing stuff into a beaker or into a chemical reaction, and we need to know if there's any free energy in there for this chemical reaction to go. So what if you had more or less? Is there a way to manipulate or change the free energy? It's hard to change the equilibrium constant unless you change the temperature. But can you make something spontaneous that wasn't spontaneous before? We run into this. What if you have a non-spontaneous chemical reaction? Is there a way to make it spontaneous, to make it product favored? Is there some tricks or tips that you can use for that? Why would we even want to consider this? I'm going to go back to our biochemical table here from a biochemistry textbook showing delta G naught here under standard conditions versus delta G under non-standard. Standard versus non-standard. Now look at the signs of delta G here in the standard conditions. Negative, positive, negative, positive, positive, negative, positive, couple negatives. It's almost like half and half spontaneous, negative delta G's, and the other half are non-spontaneous. Well, this isn't good. We need, the chemical reactions in our body need to be negative delta G's. They need to be spontaneous. That means they're going to go and make products. They're not very product favored. This is not good. So what's this delta G here? Because now when I look at it, they're all negative. All of these reactions have become spontaneous. How in the world did that happen? It comes from an understanding of how a chemical reaction behaves under non-standard conditions. You see, life is a series of coupled, that means connected, non-equilibrium chemical reactions. So we really need to understand, how did this happen? Because that allows for the spontaneous chemical reactions to take place. Okay, it's the secret to life. All right, so biochemistry helps us to understand the relevance of this topic. And so it will come back for many of you who are going to go on to biochemistry. So it's important to start learning these concepts now. One of the pictures in my mind that I like to think about, and I've shared with my students in the past, is that we like to understand the concentrations of the reactants and products under non-equilibrium conditions using this concept of Q. In fact, we just stated this when we were first teaching that if you have a system that's not at equilibrium, and you have this, we could calculate a Q, that the reaction will move spontaneously towards equilibrium. Whether you have too little reactants, it'll make more, or too little products, then the reaction will make more products. If it's too much products, then the reaction will reverse and go the other way. We just stated it. And so, but it's important to understand, to calculate the Q, which is basically the equilibrium expression, but under non-standard conditions. So hopefully the ICE tables and remembering these things will help you to understand which way we were supposed to shift, right? If Q is greater than K and Q is less than K, oh man, this is coming back again. So how can we show and prove that that a chemical reaction will spontaneously, in a negative delta G way, move to go back to an equilibrium position? So notice there's like this force that's pushing the chemical reaction back towards the equilibrium. And it's that movement that creates energy for life. Unfortunately, I can't derive the chemical or the mathematical equation here. I'm just going to just throw it out there, and so we can just use it. There is an expression that relates Gibbs free energy for a chemical reaction under non-standard conditions to the free energy under standard conditions. So here it is. If we can figure out the free energy of a chemical reaction under non-equilibrium conditions. See, there's no little naught symbol there. By comparing it to the free energy when we are at equilibrium, plus this RT ln of Q term. So here's our Q for our equilibrium quantities. And I define the terms here as I was stating them. Okay, so this delta G without the naught symbol is very important when what we want to figure out right now. How do we understand and calculate the Gibbs free energy under non-standard conditions? Okay, so they're definitely related to the equilibrium constant and under conditions at equilibrium. All right, so there's some important concepts that go along with this. One of them is when Q is less than K and Q is greater than K, we want to be able to show that the reaction is spontaneous. We want to be able to show that delta G is less than 0, is negative. And that'll help us decide whether this thing is, the reaction is going to go forward or backwards. We'll give some examples here in just a moment. So how do you figure this out? Coming up next. All right, what about if Q is equal to K? What happens? Well, if Q is equal to K, then our delta G, we're going to say is 0. We're at equilibrium. And if that's the case, then 0 equals delta G naught. That's the little degree symbol plus RT ln of K. If I solve this equation by moving RT ln of K to both sides, by subtracting it off, you can see that I get delta G equals RT ln of K, negative RT ln of K. So I'm able to derive that first equation that we talked about a few minutes ago. All right, let's put this to work, okay? So the difference here we really need to pay attention is to whether there's a naught symbol or not, okay? Naught, N-A-U-G-H-T. All right, let's think about a chemical reaction that has, and I should have had them come up one at a time, but we'll just kind of walk through this here with my laser pointer and see what's going on. So here's a solubility chemical reaction, silver chloride dissolving into silver ions and chloride ions. This is a KSP chemical reaction. Here is the equilibrium constant, 1.6 times 10 to the minus 10 for silver chloride. We can plug that into the chemical equation here to get our delta G naught at standard conditions. Here's our R, here's our T, under standard condition, here's our K. Plug them in your calculator. My Kelvins cancel out and I get joules per mole. 55,900 joules. So it's 55.9 kilojoules. All right, so this is the Gibbs free energy under at equilibrium. What is the free energy at the non-standard conditions of both of the ion concentrations being 1.6 times 10 to the minus 6 molar? As soon as you see the word non-standard conditions, we need to bring in the non-standard equilibrium Gibbs free energy equation here. Once we bring that in, we can calculate our Q because it's just the products multiplied divided by the reactants, but the reactants is solid. Concentration doesn't change, so we don't include that in our equilibrium expression. Multiply the two concentrations together. That's my Q. Now I can plug in, and it looks like I forgot a couple of zeros in here and they got moved around. So it looks like we need to fix some of our equations here. All right, I'm going to hope that we've got this working now. Got our numbers back in here. So we're trying to calculate the equilibrium constant here, or at least Q under non-standard conditions. By plugging in my two concentrations, I get my equilibrium constant, or my Q, 1.0 times 10 to the minus 12. This gets plugged into the non-standard equilibrium equation. Now I got it, and our numbers are lining up. Here I try to color code where the numbers come from. And then here's our RT ln of Q. So we plug in our Q, here's our R and T. Plug these in your calculator. You should follow along and try to do this so you can get the same numbers as me. Just pause the video and see if I'm doing this correctly. So now this second term here with the RT ln of Q, I get a negative 68,500 joules, okay, 68,500 joules. I'm going to add that to the 55,900 joules that I had from the delta G naught at standard conditions. When I do, I get an overall negative 12,600 joules, or negative 12.6 kilojoules. The important thing here is that it's a negative number, which also means, as I've written the chemical reaction, the silver solid going to, get my laser pointer back out, the silver solid going to the silver ions here, that means the way that I've done this problem, the reaction is spontaneous in the forward direction. So that's very important. That's our last note on this particular situation right here. So with these two concentrations, they're very low, and so the reaction wants to go forward to dissolve the solid. So at this point, we probably wouldn't see any precipitate or solid. All right. Now let's look at some other conditions for this and see how we would calculate the free energy. So using the same information, what would happen if the silver ion concentration and the chloride ion concentration is 1.26 times 10 to the 5 molar? Well, we go grab our equation for delta G at non-standard conditions. Let's recalculate Q. So that's what's going to change here. So we calculate the Q by plugging in our two concentrations, and we get 1.59 times 10 to the minus 10. Plug this into our Gibbs free energy at non-standard conditions. So here's our delta G naught numbers, RT ln of Q, RT, and here's ln, and then here's Q. Plug these in your calculator, and turns out that we get 0 joules. Well, how can that be? Well, it turns out these are the standard conditions for this particular chemical reaction. So when the concentration of silver and chloride are at this concentration, it's at equilibrium. For a solubility chemical reaction, that means it's about ready to precipitate. So we want to see what does that look like when the system is precipitating. So the previous one actually showed it dissolved. It wants to stay to the right, make lots of product, and no reactant. Here we're seeing we're just at that balance point where we're at equilibrium. Okay, reactions at equilibrium. So let's take a look now when we have higher concentrations of silver and chloride. Okay, let's put them at 1.0 times 10 to the minus 3. Using our Gibbs free energy equation, we see what? Well, we got to calculate Q, put it in to our non-standard Gibbs free energy, and there's our delta G naught again. RT ln of Q is what has been changing. So our new Q goes in here, and we recalculate that it is a positive 21,600 joules. Well, that's a positive number now. So this thing is not spontaneous in the way that I've written it, but if I reverse the reaction, it will reverse the sign of delta G. This is something that's very similar to what we've done with delta H, with delta S. If you reverse any of the thermodynamic properties, you reverse the sign. So it becomes positive to negative, or negative to positive. So that means the reaction is actually going to be spontaneous in the other direction. What does that mean? It's going to want to make reactants. In this case, it wants to precipitate. So the reverse reaction to make the precipitate is the spontaneous thing that happens and precipitation occurs. So when the concentration is too high of silver and chloride, you will see the precipitate. And we can prove that now with this equation that it's spontaneous to make the precipitate. So it'll keep going and keep going until it reaches equilibrium, then the reaction stops. But we will have then precipitate and still some silver and chloride ions left in solution. So this is how we use free energy and equilibrium, put them all together, and we run some problems and think through that. And in summary, what we see then is we can calculate how delta G naught relates to the equilibrium constant. And remember, delta G thermodynamic variables are important if they're positive or negative or 0. We relate that to equilibrium constants that are important if they're greater than 1, less than 1, or equal to 1. We can then go and calculate delta G without the naught at non-standard conditions and see if the reaction is spontaneous or not, and they really will be if they're not at equilibrium, okay? And so we can prove how things become spontaneous, but we've got to push them outside of their equilibrium conditions. And this usually takes some kind of knowledge of what it would be to be at standard conditions, and then what it needs to be under non-standard conditions. Because all chemical reactions are going to be moving towards equilibrium. And so if you wanted to constantly keep working, you need to tip it outside the non-equilibrium to make it non-equilibrium conditions. So how does life do this? Because if all chemical reactions are at non-equilibrium, how did that happen? We would need another class to describe that. Hope you learned a few things about chemical reactions, free energy, and equilibrium. Kind of a longer video, but this wraps up our chapter on free energy and entropy and how this all relates back to equilibrium. And so thank you for joining me, and have a great day.